Hi there and welcome back to Triplicate, and today, after some delay, we're moving on with the Radical Synth, the Heresy. Delayed partly because we were away for 6 weeks over the summer, and partly because last time we tried to redo our turntable arrangement and it was basically a fail. So we're going to have to look at that in the future, but we're going to leave it for now. And so far our sound generation have consisted of basically a sine wave, so I think today we're going to look at making it a bit more interesting. There are two ways of doing this. There are stacking up our basic sort of mass on a spring style oscillators called coupled oscillators, which we're going to look at today, and there are models of strings like in a violin, or uses the same modelling, air in a pipe like a recorder or a flute, and we will look at them in the future, but for now we are going to play with some coupled oscillators. So what we've had so far is a mass and an M. Anyway, a mass on a spring with a drive, and we take as our output the position of the mass. So with a coupled oscillator, and the simplest one, traditionally you would have, proper M this time, two masses with springs between them like that, and these will resonate. This has one resonance. So if we drive this at the right frequency, this will have a very big output, tailing off at all other frequencies. In fact, the frequency response is like that, essentially a resonant filter. But what about this? Well, we can do some mathematics. Now I did quite a lot of mathematics because I did a physics degree, but it was never my favourite thing, otherwise I would have done maths at university. And you certainly don't want to watch me solving lots of equations. It would make for a very tedious video. And there are resources online, and I will maybe list a few in the description. I will, go on. These are mostly from university, so you fancy the maths is going to be a tad heavy. So we are just going to borrow the results. So this will have two resonant frequencies, one where the masses are going opposite and one where the masses are going the same. And it turns out that these frequencies are the normal resonant frequency F and square root of 3 times F. So let's actually have a look and see if we can make a model of this, a little bit of software that'll do this, and if it comes out at the right answers. So we will actually, on our simplest case for consistency, we will have another spring to a fixed end here. That just adds in a factor of 2, and all these springs and masses are the same. And obviously we will have a drive here for this one, and we will see what happens. Okay, so let's build this up. Firstly, let's consider one mass, one spring, which is the oscillator we've got. And what we're going to do is just drive that with a swept frequency and see what happens. Okay, here it is, and we get a resonant peak. I don't really need to play you this because it's just a sine wave with a resonant peak. And if we go there, and I need to look at the frequency analysis, you can see here that's about 200 Hertz, and we've set it to be 200 Hertz. So that's what we would expect. Okay, now we've got two springs either side which are acting together. If the mass moves that way, that one's pushing it back, and that one's pulling it back. So there's twice as much spring acting on the mass now. So what would we expect to happen? Well, if you do the equation, the mathematics, which we're not going to do, we find that the frequency, and yes, if mathematicians among you, this is angular frequency, but we do not care about the odd factor of 2 pi, is the square root of k, the spring constant, how hard the spring pulls back, over m. So if we have twice as much spring, k is 2, so the frequency goes up by the square root of 2. So we would expect to see 1.4 times 200 Hertz, which is about 280 some Hertz. So shall we have a look at that? Okay, and here we are. We get a resonant peak again, and if we look at the frequency analysis, we put the cursor at the peak. Yeah, the cursor is at 280 some Hertz, so that is behaving as we wish. So now let us look at two masses. So for two masses we have two resonances, and you can do a big bunch of maths and start thinking about eigenvalues and eigenvectors, but as I say, I prefer to look at the thing and try and get a feel for what's going on, rather than just going through equations and coming out at the end and not knowing what the answers actually mean. So our two masses have two resonances. One where the masses are going in opposite directions, and one where the masses are going in the same direction. So we should get two frequencies. Now if we do the equations, we get f, which is our 200 Hertz, and the square root of 3 times f. That's predicted, so let's simulate that and have a look and see if our model is working correctly. So here we have two peaks. Let's have a look at where that one is. So that one is at about 200 Hertz. Okay, and this one is at about 340 some Hertz. So it's behaving as we expect. But two things: why this curious square root of 3 ratio, and secondly, that's not very helpful. We want a sort of harmonic spectrum. Good for making sort of clangy bell-like noises, but not for making tuned instrument noises. So if we open this, so this is just, let's get rid of that, firing an impulse in instead of a swept sine wave, a longer impulse and a shorter impulse, and this is what we get. So as I say, a sort of clangy sound, well, a sort of woody sound, but those are about 1.7 something, which is about 1/6 apart. So let's have a look at why, if we can figure out, without doing a ton of mathematics, why we're getting this square root of 3. Okay, First, let's look at when our masses are moving together. They are actually moving the same, because they're the same mass, the thing's symmetrical, they're moving the same amount together, so this spring never gets extended. So in fact we have twice that, so we get our 200 Hertz. Now what's happening when they're moving apart? Well, if we look at when they're moving in opposite directions, well, if we look at one of them, it's got the normal spring here, and here, when that's moved 1 unit that way, that's moved 1 unit that way, so that spring is getting twice as extended. So if looking at it from the point of view of this mass, it's getting twice the force that way, which could just be the same as that spring anchored, but that spring with twice the K. So in this case we've got K plus K over M, which is 2K over M, which again gives us our square root of 2K over M, which is why it was 1.4. But in this case we have 2K this way and 1K this way, so our frequency is given by square root of 2 plus 1 K over M. So it's the square root of 3 equals, sorry about getting boxed into the corner here, the square root of 3 K over M. So this is where our square root of 3 comes from. And just to confirm, our 200 Hertz peak here, they are both going the same way with the same amplitude, whereas if we look at our 340 Hertz peak, let's just zoom in a tad more, they are going the opposite ways with the same amplitude. Okay, all good so far. So shall we look at the case of 3 masses? Okay, so now let's consider 3 masses. So it's not quite so obvious here what modes we're going to get. Yes, we get them all 3 together, you would have thought, and possibly one way and 2 the other, and the one in the middle stationary and the other 2 moving in opposite directions. Again, if you do the heavy duty maths, this comes out and you get some frequencies for, I guess, our 200 Hertz base frequency. And looking over there are these at F1 equals 153 Hertz, F2 equals 283 Hertz, and F3 equals 370 Hertz. You always get the number of resonances that you have the number of masses, degrees of freedom they call it in the mathematical terminology. So let's put that into our model and see what we get. And here is the result for our swept frequency, and you see, yes, we get 3 peaks, and I think you happy to take my word for it, aren't you, that they're where we would expect them frequency wise. One interesting thing to notice is this is mass, the first mass, and this is the middle mass, and we've only got 2 channels, so this third mass is not here, but the middle mass doesn't appear in this peak here. How's that? And if we were to now to play it with our I guess impulse, we would get which is pretty unharmonic, and so on for 4 and however many. So we won't go any further for now. What we will do is we will look at this. I managed to extract the 3 resonances as numbers for the 3 oscillators. So as you can see, the lowest frequency, yes, they're all in phase, they're all going the same way, but the middle one goes bigger than the 2 outside ones. Interestingly, for the middle resonance, this is the one where we saw there was no actual amplitude oscillation for the middle one. No, there isn't. The 2 outside ones are in antiphase and nothing in the middle, and the third one is, as I suggested there might be, the 2 outside ones are one way and the middle one is the other way. Okay, so now we want to see if we can do something to make these systems oscillate harmonically, so we get an sound of an instrument, not somebody hitting the lid top of an old biscuit tin. So okay, back to our 2 mass model. So now we're going to make these masses different. So that should change the frequencies, and hopefully if we choose the right values for our masses, then that number will be 2 rather than the square root of 3. That's our aim. So we can do that fairly easy in the software, so let's see what happens. And here we are. Yeah, we still have 2 resonances and they look a lot further apart, so let's just see what these frequencies are. So that bottom frequency is 239, so that's changed, and this upper frequency, whoops, is nearly 600 Hertz, so that's made a big difference. And just out of interest, let us see what that sounds like. And we'll play the second one again, cause we didn't get much of the upper tone in the first one. Well, it's about 3 times, 2.5 times. Okay, and in addition, we'll start looking at code when we get a bit nearer, but we control the frequency of these oscillators by the integrator gain, not the mass and the spring constant, because the integrator gain is linear with frequency, gives a frequency that's linear with gain, should I say. Yeah, and here I've just put the second mass gain, integrator gain, up to 2. Okay, so we now need to find some relationship between those frequencies and that mass, and then we can convert that to a gain value when we've got that. Okay, so I have played with this quite a lot off camera. Again, you don't want to watch lots of footage of me saying so I have come up with some modifications to our little program which I will show you. So we have multi-mass harm, it's all test program, dead hacky, and we're looking at 2 masses. So here we can set an increment, and we can change 3 harmonics by this increment, so we can sort of zone in on where we want to be. And at the minute we only have 1 harmonic, so 2 and 3 are not in use. I could write code that disables them, but I can't be bothered. It's only test code. So we have harmonics of 1. Right, that's harmonic 1. Harmonic 0 is always set to 1, because once we get the ratios right, we can scale the thing up and down easily, and just makes it easier. So okay, we said the ratio of the first one to itself is, this is the ratio of the second one to the first. Okay, it's the ratios to the first one. Obviously the ratio of the first one to itself is 1, again test code, don't really need to put that, and the second one is 1.7 because both the harmonics are 1. So if we increment our harmonic, so it's 1.1, and fire that up, we get a ratio of 1.7172. We're going in the right direction. We will try 1.2, 1.76, 1.3, 1.86. We are getting there. 1.4, 1.96, looking good. 1.5, hey, 2.07, 2.08. Well, that's near enough, because we're just looking for the top of the resonant peak in the sweep, and then we can't measure it that accurately, so that is near enough. So let's run it at 1.5 and 1 and see what we come up with. So if we go into here, so we've got 0 and 1, and we're going to do that to 1.5. I find it works better just for testing if we have the highest frequency mass, as it were, nearest the drive. So that's wrong, idiot. So it works better if we put the highest frequencies near 0 where the drive is. We won't bother with that, we'll just accept it. So now if I run that, and we just run the standard test here, okay, so that's done, and if we load it into here, ignore that. So we get our sweeps at, let's run this here, two to 8 and 259, pretty reasonably accurate, but as I said, we can't tell, that's not that accurate. So let's hear what we've got for our plucked one, which will play the harmonics together. So what about 3 masses? Can we find the harmonic values for 3 masses? Well, here we are, and those are the values for 1 and 1. Again, harmonic 3, ignore. So alright, I have played with this, so I'm not going to be here forever and a day trying to guess it, but if we try harmonic 2, that one. So we're looking at 1, 2, 3 here. So that's 2.4. If we increase it, try it again. 2.5. Increase it, try it again. 1.6, here we go. There you go, 2.0 and 3. So is that right? Is that the one? So that's 1, 1 and 1.6. Should we... well, we'll just try 1.7. See what that gives us. Yeah, that's way out. That's high. So 1, 1 and 1.6. Shall we try that and see what it sounds like? Okay, we hit that. And that's done. So we will load into here. Right, and we're interested in this little guy at the end to see whether that is in tune harmonics. So should we play it? Yeah. Sounds like it. And if we zoom in, sorry, the waveform repeats, so the harmonics are multiples of the fundamental frequency. So we have 3 masses. Shall we try 4 masses? Okay, so here we are with 4 masses, and I've fiddled this. This is the one at the bottom. As you can see, I've created an error value, and that's the lowest I can get. Whether it's a completely different combination that produces a better lower error, I don't know. And as you can see, it prints out the frequencies here and with the ratios of what we're interested in. So it's 2.033, 3.0003 and 3.9985, and bearing in mind a semitone is 5%. They're not super brilliant. It's not going to be, you know, perfect harmonics. So shall we see what it actually is going to do? Okay, and here we are. Let's hear it. Yep, you can hear the first 2 harmonics aren't perfectly tuned, so it has that slightly sort of gongy belly tone. Is that a bad thing? I don't know. Right, well, just for the laugh, I am going to try 5 masses and see what we can do with that. Okay, so I've done it for 5 masses here. I've changed the software so we can set another one and just gone through each in turn, getting the least error, and then round and round and round till that's the best I can get it. And you can see they're not brilliant at that. So let's hear what they sound like. So they're not, as I say, great. There's still a sort of ringing noise. So I think we need to do a bit of rethinking here. Well, okay, I think I'm going to leave it for this video here. Now, it was not quite as easy to do these coupled oscillators as I thought it would be, and I thought it would be a nice easy way of getting away from using basically a sine wave. but it's been interesting, so we might persist with it, but there is an alternative. However, there is also an alternative which sidesteps all this complicated maths of coupled oscillators, and that is doing it this way. So we have our drive here, our spring and our mass, and then we have now you draw this, call it an amplifier, which drives the spring to the next mass, and then an amplifier which drives the spring to the next mass. So each of these masses on a spring is independent, and so we can set them to whatever frequency we like. So we can get exact harmonics that way, but I would rather use the coupled oscillator method if we can get it to work better, because it's more fun and it's more sort of unpredictable, and you know, like the way a real instrument would work. So before the next video I will do some head scratching and thinking, and hope I have some inspiration of how to work these coupled oscillators out to get a harmonic response. I did think doing 3, 4 and 5 it would become kind of obvious, the pattern of the numbers, but it isn't. So there you go. As I say, I will pursue it. However, that's it for this video, so for now it's goodbye from Triplicate. Goodbye.